Hi, my name is Zhang. Today I'd like to give a presentation about our paper. The title is FuzzyKey, Comparing Fuzzy Cryptographic Primitives on Resource-Constrained Devices. First, I'll show the context of implantable medical devices, which are IMDs in short, and wearables. The IMDs and wearables are extensively used nowadays. These devices have in common that they rely on a wireless interface to communicate with each other or with external devices, for example, an IMD's programmer device. This can bring much convenience to users. However, it also poses new security threats. For example, if an adversary can alter the commands sent from a programmer to a patient's pacemaker, the patient's life can be at stake. It is necessary to bootstrap a trust with these devices to protect the wireless communication. However, this isn't an easy task for them. First, these devices generally have limited computational power and memory. Second, they also have limited battery capacity. In particular, most IMDs are operated by a non-rechargeable and non-replaceable battery which typically lasts for years. Once the battery is drained, the IMD is replaced through a surgery that can pose risks to patients. Similarly, wearables typically contain small batteries such as button cells. Third, they often do not have any physically accessible input or output interfaces, such as a keyboard or screen. Fourth, the network connections with these devices are not always static. For example, in an emergency, a doctor may use a totally new programmer to connect with the patient's IMD. This process can be vital to the patient. For this scenario, conventional key exchange solutions are often not viable. Take an IMD as an example. We can't embed a symmetric key inside the IMD during manufacturing, because in an emergency, the external device may not have access to this key or have stable internet connection to retrieve this key. It's also hard to apply public key cryptographic because it requires to establish a worldwide, robust and costly PKI. Besides, an external device can be compromised. For example, a programmer can be stolen by an adversary. This requires an IMD to have a mechanism to revoke such illicit devices. However, an IMD always doesn't have internet connection for such updates. Unfortunately, many medical and wearable devices available on the market currently lack security mechanisms and are vulnerable to different kinds of attacks. To address this problem, researchers have proposed to use human physiological signal, which is PS in short, for key exchange between two body area devices that do not have any prior trust relationship. The principle of this solution is that two devices can agree on a key by independently and synchronously taking a measurement of a given user's PS. We want to note that the PS must satisfy four main properties to be used in crypto protocols. It must be available under any circumstances for the devices that are attached to the patient. Besides, the PS must remain inaccessible unless the Marin device makes physical contact with the patient. Moreover, the PS must contain sufficient entropy. Otherwise, it will take a long measurement time to derive a key from it. Furthermore, the measuring devices should be able to obtain very similar measurements, even if they are attached to different positions of the patient's body. Here, we also note that PS is different from biometrics, such as a fingerprint, because PS varies over time, while biometric is to some extent invariant. The main problem of this solution is that the measurements of two devices are often not identical, but at best rather similar due to inherent noise introduced by the measuring process. The solution is to use fuzzy cryptographic primitives, which allow two devices to agree on a cryptographic key from several simultaneous and noisy measurements of the same signal. These methods have become the basis of many PS-based cryptographic protocols. Here, we'd like to briefly introduce the most common fuzzy primitives used for PS-based key exchange. We recommend you read our paper for more details about these methods. First, let's introduce fuzzy commitment. Both the transmitter and receiver measure a PS and generate a bit string from it. Next, the transmitter generates a random session key and encodes it using an error correction code. Then, the transmitter masks the code word by XORing it with the PS string and sends the result, which is FC here, to the receiver. The receiver will XOR FC with his PS prime measurement and decode the result to obtain the original key. The principle of the fuzzy commitment is that the key can be concealed by the PS data, while the mismatch between PS measurements can be eliminated using an error correction code. Next, let's introduce the fuzzy vote. Different from fuzzy commitment, here the transmitter and receiver measure a PS and convert it to a set. Next, the transmitter generates a session key and embeds the key into a polynomial. Then, the transmitter generates valid points that are on the polynomial using PS, and also generates a large number of random invalid points that are not on the polynomial. Later, all these points are mixed and sent to the receiver. The receiver will try to match the points according to his PS prime set, and execute polynomial reconstruction to reveal this key. The principle is that the key is concealed by a large number of invalid points and can only be retrieved if the receiver has a similar enough set. For the fuzzy extractor, the principle is that both transmitter and receiver measure a PS and correct the mismatch by sharing so-called helper data. Afterwards, both sides use the agreed PS to extract a session key using a strong extractor, for example, a secure hash function. There are four main constructions of fuzzy extractor, namely code offset and syndrome constructions for Hamming metric, and improved Jules-Soudan and pin sketch for set metric. Because of the time limitation, we won't describe each of them in detail here, and we recommend you read our paper for these details. The security of fuzzy primitives has been studied extensively in the past. However, we noticed that there remain several questions. For example, it remains unclear if it's feasible to use the fuzzy primitives on resource-constrained devices. Besides, which ones are most suited for PS-based key establishment? For our work, we address these research gaps. We implement PS-based 128-bit key establishment using 6 fuzzy primitives we just mentioned, and provide open source codes under an MIT license. We fully evaluate and compare the fuzzy primitives on resource-constrained devices. We also make constant time optimizations on the most efficient variants and test the effect. Moreover, we study how the performance of fuzzy primitives of the same security level can be affected by different parameter selections. To fairly compare and evaluate different fuzzy primitives for PS-based key exchange, we make several design decisions. First, it's necessary to make assumptions about the similarity of the PS data obtained by two devices, which are the inputs of the fuzzy primitives. In our paper, we modeled the PS data using 3 predefined mismatch thresholds as 2%, 5%, and 10%, according to data reported by some prior work. The mismatch rate indicates the percentage of different bits of 2-bit strings or percentage of different elements of 2 sets. Moreover, error correction code is frequently used to achieve error tolerance in this paper. We use binary BCH code and RS code as the underlying error correction codes of the fuzzy primitives. These codes were recommended in the first papers on fuzzy primitives. Furthermore, we chose Hyros as the strong extractor required by all fuzzy extractors. Hyros is a block cipher-based hash function. In this paper, we chose Hyros because we can use AES as the underlying cipher to leverage the hardware AES accelerator featured by a lot of low-power embedded devices. In our work, we evaluate and compare each fuzzy primitive and the various parameter selections. For each fuzzy primitive, there can be multiple feasible parameter choices under the same mismatch rate. For example, using different configurations of error correction codes may achieve the same error tolerance. For example, the fuzzy commitments with 50, 44, 1 and 200, 168, 4 BCH codes as the underlying error correction code can both address 2% mismatch rate of the PS. However, the former is expected to use less computation and consume less energy. However, it can only distribute 44 secret bits each time, while the latter can distribute 168 bits each time. To establish 128 bits secret, the former fuzzy commitment needs to be executed for 3 rounds, while the latter only requires 1 round. We want to study how parameter selection affects energy consumption performance in this way. Therefore, we test different variants under the same error tolerance and implement 22 variants in total for Hamming metric methods with different underlying error correction code settings. For set metric methods, we observe that there can be many more possible parameter choices. Therefore, we only implement 3 variants for reference, and note that one can refer to our work and devise more appropriate variants for set metrics with specific mapping from PS to set. Next, I'll describe the implementation details of our work. We implement all fuzzy primitives in plain C and mainly rely on standard C libraries so that our implementation can be easily ported to different platforms. We refactor our codes using TI Ultra Low Power Advisor tool to minimize the energy consumption, and run all algorithms on TI MSP430 development kits, which are representative low-power microcontrollers similar to the ones used in commercial IMDs or wearables. We carry out the accurate on-device computational energy measurement using TI Energy Trace tool, and model the cost of various communication of each variant based on experimental results of prior work. In our context, it is possible that an adversary can accurately measure the execution time of the programs and exploit timing leakage, thus reveal the secret to some extent. Therefore, it's necessary to make constant time implementations for the key exchange. In our work, we make constant time optimization on the most efficient variants. For example, we replace a few conditional branches with Boolean operators to make them constant time. We also apply some techniques such as constant time modulo, reduction, and constant time sorting. We further verify the effects of implementing these optimizations, including the effect on timing leakage and energy consumption. The results show that our optimizations reduce timing leakage below the statistical significant threshold, while only minimally affecting energy cost. For example, here we show the optimization effect on the transmitter side of a syndrome extractor variant based on 3129.1 RS code. For the timing leakage testing tool we used, if the t-value is smaller than 10, the timing leakage of the code can be regarded as insignificant. It's interesting to find that the energy consumption even decreases after applying the optimizations. This is because we use barrier reduction to realize constant time modular reduction, and this replaces the original costly operation based on division. Next, I'll show the evaluation and comparison of the energy consumption performance of all fuzzy primitive variants. We conclude and provide precise data of each variant for reference. Here, we show a variant based on 5044-1 BCH code as an example. All three kinds of hemi-metric fuzzy primitives, including the fuzzy commitment, code offset, and syndrome fuzzy extractors, require 3 iterations and 150 bits PS data to achieve 128 bit security. We also show the computational energy consumption of both transmitter and receiver size, as well as the communication burden of each fuzzy primitive. We include such data of all variants in our paper, and we believe that these data can be valuable reference to real-world protocol designs. This figure shows a general trend of the energy consumption results of hemi-metric fuzzy primitives and the different mismatch rates of a PS. And this figure shows similar information for set metric methods. We include precise analysis of these data in our paper. From this data, we can observe some common tendencies for all fuzzy primitives. For example, for each variant, the energy consumption for the receiver is generally higher than that for the transmitter. This is useful in certain scenarios. For example, a low-power IMD can act as the transmitter to minimize the energy consumption. Besides, the energy consumption of variants with smaller parameters, such as using an error correction code with a smaller block, generally consume less energy, even if more iterations are needed. Overall, we show the most efficient variants of the fuzzy primitives in both hemming and set metrics and their different mismatch rate thresholds. We observe that these variants consume between 0.021 and 0.198 mJ for the transmitter side, and consume between 0.029 to 0.38 mJ for the receiver side, including both computation and communication cost. This energy consumption data is comparable with Curve 25519 running on the same hardware setup, which consumes 0.404 mJ for one full execution. We want to note that Curve 25519 is one of the most efficient elliptic curve-based key exchange schemes for embedded systems. Here, we also note that compared with Curve 25519, the PS-based key exchange can naturally defend against man-in-the-middle attacks and guarantee that the receiver and the transmitter devices are in physical proximity. We conclude our work in the end. To the best of our knowledge, we are the first to compare the computation and communication energy consumption of different fuzzy commitments of different fuzzy primitives for a variety of parameter choices. We demonstrate that PS-based key exchange methods using fuzzy primitives are feasible for resource-constrained devices such as an IMD or wearable. We recommend to use syndrome and pin sketch fuzzy extractors in hemming and set metric spaces respectively, instead of the fuzzy commitment and fuzzy vote that were frequently used in previous PS-based key exchange solutions. In general, our work serves as a reference when applying fuzzy primitives for body array networks and medical devices, and we believe our work is also valuable for other use cases such as biometrics or PUFs. That's all for our presentation. Thank you so much for your time to listen to us. We also leave the GitHub link and email address. Please don't hesitate to ask any questions. Thank you.